just enjoy the hard work, just to let a man know that a woman still can run with him.
Once one side of the drawbridge section has been welded, the next difficult task is to flip it over to weld the other side. This girder weighs over 90 tons. Two 50-ton overhead cranes are used to roll the girder to make sure that neither one is overloaded by this massive piece of metal.
This is a very critical lift. On this project, there are 16 girders of this size. Each one of them will be rolled one time.
This is a trunnion girder, which will eventually hold the pivot around which the drawbridge will hinge.
This is the most critical part of the move. The girder is now vertical. We are using blocking to start the rolling process that will start the girder to tilt out of the vertical position. Then the center of gravity will take over and the girder will lay back over with the far side up.
Amazingly, the whole process of rolling this metal monster takes only 5 minutes and is made to look easy. As the work continues in Florida, back in Washington, the engineers are anxious to receive the drawspan sections.
Lots of trepidation because this whole thing's been done on paper. I mean, it's been all laid out. I mean, the pieces have been constructed but never put together. So everybody hopes that that measurement is precisely right when that piece gets raised, that the holes will line up and they can put the bolts in. And we hope nobody made a mistake in the process.
To ensure that the drawspan sections will fit at the job site, they're fully assembled and checked for alignment in the heavy fab shop in Palatka, Florida. Each section weighs a massive 1,600 tons and takes 5 weeks to bolt together.
Right now we're standing inside of one half of one of the bascule bridges of the Woodrow Wilson project. The total tonnage of this structure that we're standing in here is about 1,600 tons. Right above us here is the trunnion, and this is what this leaf rotates on when it opens up. The wire that you see that's going through the trunnion is a piano wire that we use for a gauge that is checked daily to assure that we're holding all of the dimensions, vertical, horizontal, and lean within the dimensional tolerances as we continue to erect through the bridge. Inside this massive structure, we're only allowed to be 5/1000ths of an inch out of tolerance. Vertical, horizontal, and any tilt.
If the bridge builders have got these precise measurements only slightly wrong, there's a serious chance that the drawspan will not fit when it gets to Washington. The other major worry is that outside the heavy fab shop, the storm clouds are gathering and the hurricane season is only days away. Because the bascule or drawbridge sections of the new Woodrow Wilson Bridge are so huge, the V-piers which will hold them have to be extra large and have to be cast in place on the river. There is no crane big enough to assemble these giant structures from precast segments. So 40,000 cubic yards of high-strength concrete have to be poured into the superstructure of each mammoth V-pier. The concrete is piped from the Virginia shore to fill the steel structure as it climbs into the air. The concrete is poured into green reinforcing steel bars, which physically hold the concrete in place and give it additional strength and flexibility. While they're under construction, the bascule piers are supported by what is known as falsework, metal structures that hold the concrete in place until it solidifies.
On the other side of the channel is what we call the falsework, or the scaffolding for the construction of the cast-in-place piers. And it's really a significant effort due to the size of the piers, the weight of the piers, trying to produce this shape very precisely out over the water, leapfrogging the forms up for the next pour, just basically working our way up the legs.
Creating structures this complex and on this scale is pushing the limits of what can be done with concrete.
With massive structures like this, it's much harder to work with the concrete. Concrete generates an extreme amount of heat. The interior of the concrete wants to get hotter than the exterior of the concrete. So we run cold water through cooling pipes to regulate the temperature of the concrete after we cast it. And that allows us to maintain an equal temperature from the outside of the concrete to the inside. If we don't keep the concrete cool, it will develop what they call thermal cracks. Cracks that are generated just from the sheer heat. Even with our cooling pipes, the concrete will get to around 160 degrees. If we didn't have the cooling pipes in there, it would get in excess of 200 plus degrees and causes a lot of trouble.
Two of the bascule V-piers are almost complete and have some of the massive moving parts of the drawbridge already installed.
Behind me you can see some of the machinery involved in moving the bascule span, and that's really where our fixed structure meets our movable structure. Well, the bascule is basically a balanced seesaw or teeter-totter, like when you were a child on the playground. There's a motor that drives a gear that literally rotates the span about a hinge, and that allows us to move the span up and down and rotate it to allow boats to pass through the channel.
At the back of the hinge is a massive counterweight box.
Right now I'm standing on the counterweight box, which is the balance point for our draw span. These access holes that we see, one that I'm standing on, allow us access to the interior to place the steel and the concrete that act as the dead weight for our balance.
Back in Florida, the first massive bascule section is finished and will soon be ready for transportation. But in order to move it, it first has to be broken down into smaller pieces.
We've actually assembled the whole bridge just like it'll be assembled in the field. And then we take the bridge back apart and we paint it, and then we move it down to ship it. And this particular project is being shipped by barge. Because of the size of these pieces, barge is the only way that we can ship them. And there's no way that you could ship those by truck or rail.
The PDM plant at Palatka has its own dock on the St. Johns River.